Small talk as we get started here. 1 minute before let's start the recording, just doing a little volume check. Okay, cool. Yeah, I know this is not an easy format for, I'm sure, for all of you. So thanks for, um, yeah. All right. Let's do that. Let's move this here. Do that. Okay. All right, all right. Let's see. Wednesday, April 29th. Um, all right. I want to just do a quick run through of some of the ideas from yesterday. I don't want to belabor it too much, but say you start with a set of cardinality n, then the k permutations. So this was choosing, and it's kind of unfortunate the word choosing I get, right? But choosing k elements where order matters. Choosing k elements where order matters. Okay, that's what k permutations are. You have to pick k of the things, but if you just take those k things, you switch up the order, that's considered a different permutation. The number of ways to do this, we won't prove it again. Just write down that notationally we call that p of nk, and that this was n factorial over n minus k factorial. The other thing was k combinations. And this is choosing k elements where order doesn't matter. This is more typical. Order doesn't matter in just like actual applications of things. And that's why I think the number of ways, well, we can use this notation C of nk, but I think that's why this one was chosen to be called n choose k. I mean, both of these have the word choose. And we had discussed yesterday how should be the number of permutations, but that's number of permutations overcount by a factor of k factorial. As a note, we had said some of these things yesterday, but I just want to remind you, because I think they will kind of come up in just little moments today, that p of n is n factorial. So this is like, imagine you have a deck, a standard poker deck, 52 cards in the deck, and how many ways you shuffle the deck, and then you shuffle another deck, and how many different shuffled decks can you create? 52 factorial of them. So all n elements of your set participate, and if order matters in shuffling, it does, right? There's n factorial. Like if you had 52 factorial plus 1 decks of cards, no matter how you shuffle, there's going to be 2 decks that have to be identical. P of n1 is n, and we'll see this again actually right here. C of n1 is also n, so n choose 1 is also n. Now, if you're only picking one thing, P is where order matters and C is where order doesn't matter, but there's only one thing. So there's not really much order here. So I'll talk about it over here. So of course you can just compute using the formula up there and you'll get n, but I think the key thing to do is let's talk about it more situationally. The idea here is like, let's say you have a menu. A menu has n choices. You may pick one. You may pick or choose one, right? So how many ways, right? There's n ways. There's n choices. You're only allowed to pick one thing. There's n ways for that to end. And then C of n, or rather n choose n, this ends up being 1. Okay. One of the ideas I wanted everyone to think about, especially previewing next week, is think about n times k versus n plus k versus C of nk versus P of nk. So I want to just hint at some of the big ideas. Like here are the thoughts that go through my mind when I'm trying to figure out which of the four counting methods we have currently apply. So is it product rule? So I'm trying to use n's and k's to match kind of the n's and k's here. I know that earlier we've used like a's and b's, but just because these four counting methods get confused for each other. What's going on with product rule? Well, the situation that I see is something like, and to try to, I know using this word choose might actually almost make it more confusing, but I want to kind of bring it up here. But choose one thing from a menu with n options, and then choose one thing from a menu with k options. And you have to do both tasks, right? So then the total here should be n times k. If you have to choose one, so this, if you really want, you could call this one over here an n choose one, and you could call this a k choose one, and that's what this discussion here was about. That n choose one really is n anyway. N choose one simplifies to n. So n options for the first, k options for the second, n times k kind of, don't want to use the word combination, but configurations, right? If you have to choose one thing from a menu with n choices, you have to choose one thing from a menu where there's k possible selections. In total, there'll be n times k. The sum rule. So that's to address this n plus k business now, right? So you have a menu with n options and a second menu, a menu with k options. But you only get to pick one thing, like not from each menu. You choose one thing, and to really emphasize this, I'm going to say from one menu. So then you're either picking from the first list or the second list. You might as well just pretend the two lists are combined into one bigger list. So the total number of ways to do this should be n plus k. Right? So these are the kinds of, how do you even sort out product rule versus sum rule? Think about whether you have to do two things or whether you only pick from one or the other, right? K combinations, that's the next one, right? So this C of n k. So here it's a lot more typical than k permutations, I will be honest, but like let's talk about it, right? So there are n options or contestants. I mean, there's like n things to choose from, whether these are n options on a menu or n people who want to play on a basketball team, or just, there's n things to start from, and then you have to pick k of them. Here, order doesn't matter, right? So then the total number of ways to do this should be n choose k, or C of n k, either way you write it. And then the k permutations business, this doesn't happen all that often, but it's just worth mentioning. You have a menu, let's just say, or again, it's n options or contestants, but I'll just phrase it in menu language. I want to keep changing it up, right? So what you used to, this is kind of common-ish thing in math with word problems. It's like there's many situations in which the same model applies. So you have a menu which has n options. Okay, you have to pick, let's say, k courses. Order matters. I'm calling this one a menu. It's one of those fancy menus where there's several courses. Let's say order matters, and no repeats. So your second course can't just repeat your first course or something like this. So then the total number of ways this ends is p of n comma k. I think maybe an approach for this would be like you have n people running a race, and then if they're going to publish, let's say in the newspaper, the top 10 finisher, the 10 fastest finishers of the race, how many different ways could, the next day the newspaper publish results? Well, if the order matters for those 10 people, that it could be this. But so there's lots of these, and I think the challenge here is to try to come up with your own. I mean, like, based on this text here about how to choose which of the four counting methods would apply, try to come up with counting problems that that really dig into how are these different, and think about the wording of your own question to try to not completely give it away right away, but that the things you would say would include enough information for that. I say this come up with your own because let me preview a task next week. I'll just let you know right now that next week, this is actually going to be a fairly typical question type, and it's challenging. Don't get me wrong. But let's say you're given, these will be all understood to be integers, n, k, and r. Let's say n is greater than or equal to k is greater than or equal to r. Then describe a counting problem, right? So you have to, come up with a question. There's many possible correct answers, but come up with a question that starts how many ways are there to, or how many, fill in the blank. Counting problem whose answer would be n choose k times k choose r. Now, I'm not going to give you an answer right here, right now. I want you to think about it, and we will discuss it in class next week anyway. But I just want to note just even a feature about this expression that's written down. You'll notice there's two uses of combinations already, right? There's two binomial coefficients written and a product rule. So this with a product rule as well. Right? So what the hint, I guess, then, I'll leave it to you to think about right now. I don't want to give it away, but think about, it's a product rule, that time sign here, right? So you want to think of like, where is there going to be a situation where I have something, a process has to get done and another process has to get done. And the first process involves choosing k things out of a total of n options. And the second process is choosing r things out of a total of k options. These are the kinds of things that, even as you stare at an expression like that, those are the kinds of things I want you to think about. I'm going to give you actually a completely different example, and I'll work this one through. So I'd like to describe for you a counting problem whose final answer is 10 to the fourth plus 10 to the fifth. Now, there's many possible counting problems you can come up with, but well, here's the one I came up with. So to increase security, banks in Canada now allow customers to keep their 4-digit banking PIN or change to a 5-digit PIN. How many pins are possible? So just to discuss, I mean, like here it's sort of like the question and answer are backwards from each other, right? Like the sort of Jeopardy situation. But the whole point is just to make sure we're clear about some things here by the product rule. There are 10 times 10 times 10 times 10 pins of length 4, right? Right? Because again, where did the 10 come from? So that's sort of implicit. It's not like directly stated in the problem, but here's where you gotta make some sort of, there's a little bit of use of kind of everyday something that pins are typed on an ATM using the number pad. And so 10 choices for the first digit and 10 choices for the second digit, and each choice has to be made to create a pin. So 10 times 10 times 10 times 10. Similarly, by similar reasoning, there are 10 to the fifth pins of length 5, right? So 10 to the fourth, 10 to the fifth. And then the point is, think about with these two numbers, with the 10 to the fourth and the 10 to the fifth, do we need to add these or do we need to multiply these to make sense of how many pins there are? Think about how the sum rule applies. So I'm stating the sum rule applies, but just to write something about it, because the customer has either a length 4 pin or upgraded to a length 5 pin. Right? The customer doesn't have both a length 4 pin and a length 5 pin. It's not both. It's you either keep your length 4 pin or you have a length 5 pin. So you choose from either the menu of all these pins of length 4, that menu is this long, or you choose from the new menu, the second menu of pins of length 5, and that menu is this long. And you only get one choice. Right? So those are the kinds of things that you'll see even in 10 to the 4th plus 10 to the 5th. There's product rule, there's product rule. In fact, even in 10 to the 4th, isn't it kind of multiple product rules in a sense? But let's just say there's a 4-factor product rule, and then there's a 5-factor product rule, and then there's a sum rule as well. So there's this thing of like combining these in sort of meaningful ways. Are we okay with that? Just in terms of thoughts, reactions, and this sort of thing? And these take getting used to, and I do still need to design a homework set, and I will post that tonight or tomorrow morning, just for the final homework of the semester. Yeah, these counting things take some getting used to. Okay, well, I'd like to then talk about the next section. This is actually, I think, a really neat idea. Counting with bijections. Okay, so up until now, this chapter 6 actually hasn't dealt much with any of the things from else the rest of the semester so far. Much, right? This section does a little bit with functions, but nothing too bizarre. Okay, I know that functions are challenging, but nothing as busy as we've already been looking at. Just as a quick reminder, in this chapter, all theorems in chapter 6 are about finite sets. Okay. Of course, bijections and stuff in general can talk about infinite sets, but like in chapter 6, we're only looking at finite sets. So here's the situation. Here's what this section 3 of chapter 6 is about. Someone describes to you a finite set. Describes a finite set X. So somebody describes to you the set X. It's clear to you just from how the question is worded that the set is finite, and you are asked, what's the cardinality of X? So how many things are in X? And maybe you don't know, right? It's not that you're not sure. You are not sure what the cardinality of X is. You're not sure what the cardinality of X is. But you notice the following thing. You can make a bijection from, let's get a little, you can make a bijection from X to Y. And luckily, the cardinality of Y. What can you conclude? And it's almost silly. You've done so many harder things now. But what do y'all think? What can you conclude here? Someone describes X. It's clear that X is finite. You notice that there's a bijection between X and Y. Like you can make, you're like, oh yeah, here's a bijection from the set X to the set Y. You know the cardinality of Y. You would conclude. Help me out. X is equicardinal to Y, right? So that's direct application, right? Yeah. So if these have the same cardinality, then cardinality of X equals cardinality of Y, right? These should have the same number of things. Yeah. Thanks for that response, right? So this gives you a way, like even though maybe at first it was unclear how many things are in the set X, now you have a way. So we're actually going to build bijections, but these are, don't worry, like compared to the bijections you've been asked to do lately for the cardinality stuff, these bijections are way more concrete. And I want to show you what that looks like. I want to model this just with example after example today. So here's a question. Let capital A be the set, just to keep things not too bad here, just 1, 2, 3. Set with numbers 1, 2, 3 in it. That's not the x over here, because we already know. The x I'm going to use for this problem, let x be the power set of A. And let y. So I'm trying to use capital X and capital Y in the same way as just was stated up in the discussion here. And let y be the set of all bit strings of length 3. So just to make sure we're clear about this, like just what's in y. So for instance, 0, 0, 0 is a bit string of length 3, so this belongs to y, and 1, 1, 0 belongs to y, and so on, like that. So let me describe to you a bijection. I'm going to show you right now. This one's a little bit more in words, right? But a bijection, this is truly, you can make this, I'm going to speak a little informally. I mean, it's still fairly formal, but you can make this as formal as you want. I mean, if you want me to increase the formalness of this, I can keep doing that. But I hope you're convinced with what I'm saying that we really will have a bijection. So the most natural bijection to me, there's lots of options actually, but the most natural bijection to describe that I can describe, it goes like this. So given an element, so I want a bijection from x to y, meaning my x is the set of inputs. So given an element in x, I'm actually going to call that element capital T. By the way, if you have an element that's in x and x is the power set of A, then this thingy that belongs to x, this capital T, has to be a subset of A, right? By definition of power set. So given this, we know that T is a subset of A, and then I'm going to tell you this bijection, and I'm sort of implicitly naming the bijection F. So what is F of T? Let this be the bit string. And to talk about that bit string easier, I'm actually going to name the individual bits of the bit string, B sub 1, B sub 2, B sub 3. Where? And then here's how, like one bit at a time, one like entry of the bit string at a time. Let me describe. So the ith bit, so B sub I is, it's either a 1 or 0 because it's got to be a bit. And so you're going to have a 1 if if little I belongs to T, and a 0 if little I does not belong to T. That actually right here, let me box it to be clear. That is my description of the bijection. In case it's not clear, let me provide some examples though. So this is, in the box is the actual description. But for example, the set 2, 3 maps to, okay, so this right here is like is a capital T, right? So that's a subset of A. And the first bit, so what's B sub 1? It's a question of, so B sub 1, the 1 is I right now. So it's a question of, is I, or that is 1 an element of T or not? I mean, in the set, is 1 present or absent? Well, since 1 is absent, we'll put a 0. The next thing is a 2. Is 2 present or absent? Present. 3 is present. As another example, the set consisting of 2, that's a singleton, right? This is my next example. It's a capital T. It is a subset of A. And what does F do to this? The output is the bit string 0, 1, 0. Right? So this 0 says 1 is absent, this 1 says 2 is present, and this 0 says 3 is absent. The subset 1, 3. This maps to 101. Are we clear what's going on with this description of this bijection over here based on the three examples? I'm going to pause for a minute, see if there's questions that can be answered. Maybe I will sort of then ask you all, it's not in my notes to do, but let's just do this. Why don't you think about what f of that is? So what's the output bit string you get for the set 1, 2, 3? What's the output bit string you get for the empty set's also a subset of A. Empty set's a subset of any set. Are we good with that? 1 is present, 2 is present, 3 is present, so we get a 1, 1, 1. And now in the empty set, 1 is not present, 2 is not present, 3 is not present. We get 0, 0, 0. Okay, I'm not here so much proving to you that you have a bijection, but I hope you can feel that this is a bijection, right? So every bit string of length 3 really ends up as an output. I mean, we can actually go through a proof of injective surjective. It can be done, but I'm not going to do it right now because I want to I want to step back from proving bijections for a moment and talk more about this bigger process and look at another example and so on. So what I want to do is say, okay, let's just say that we would prove this as a bijection. Then what I want to do is mention, I want it to fit the format of this situation up here, that we know the cardinality of y. So by the product rule, so remember y was a set of all bit strings of length 3. We already know, we had discussed this anyway, that the cardinality of the bit. So this is product, right? Like every entry, you have two choices here for this entry, two choices, so 2 times 2 times 2. In other words, 2 to the third. So the cardinality of x is 2 to the third as well. And actually, similarly, I mean, there's nothing really special about 3 other than I didn't want to pick a first example that's so big. So if I change up A to be the set 1, 2, 3, 4, 5, 6, then I hope you can see that you can define a very similar, bijection in a very similar format. So for instance, this subset, so my x here is again the power set of A, but then this subset should get mapped to 0, 1, 0, 0, 1, 1, right? And since there are 2 to the 6th bit strings of length 6, I hope you can see from here that the cardinality of x, in other words, the cardinality of the power set of A here, is 2 to the 6th also. 2 to the 6th 2. Okay, more generally, this kind of goes back to a thing I promised actually a long, long time ago. This was when we were meeting in person. Just to mention, this was just it was just provided as an offhand comment to try to help better explain what the power set was at the time. But now we can go back and this idea here applies in general. So if A is a finite set, again, finite is key, finite set of cardinality n, then the cardinality of the power set of A is 2 to the n. Do we feel kind of okay overall about that before looking at a totally different kind of example? Question here. If you don't know the cardinality of x, but x was built from another set A, then why was it necessary to introduce a new set y? Okay, so the whole point here was I wanted x to be the set of subsets of this set. That's all. Right, so the A has cardinality 3 plainly by seeing that there's 2 commas, right? But what I wanted to do was talk about how are there the same number of things in the bucket consisting of all the subsets of a set of cardinality 3 and in this other bucket of strings, bit strings of length 3? So sorry to bring up an A as well, but I needed X to be a set. I needed X to be the set of subsets, so that in both cases there are 8 things. Yeah, for I mean, yeah, exactly. It's just what I needed for it to work out, because this set A only has 3 things in it, and set X and set Y both have 8 things in them. So yeah, I mean, I could have instead of writing it this way, I could have just written let X equal power set of this. I just thought it looks a little more confusing to write it that way, is all. So, okay, I'd like to look at a very different kind of example. Yeah, so for demonstration purposes. Again, I'm just trying to, I wanted the capital X and capital Y to notationally match the generic situation that was described. Okay, here I'd like to try something really different. I'd like to answer this question. So I'll just phrase the question and we'll sort out what's going on here. How many north and east paths will abbreviate this N and E, or any kind of abbreviation like this will be fine. N and E paths, N for north, E for east, are there, starting at the origin in the plane and ending at 5, 3. So this is a very geometric looking problem. So before trying to even attack the question, I better explain what the heck I even mean by a north and east path. So by a north and east path, again, not like a formal definition. I'm not going to quiz anybody on what this definition is, but I do want you to know what it is, so so that we can count here. So we mean a path that moves north 1 unit at a time. I think this phrase "at a time" is sometimes confused by people, but I just mean like you do a step, and that step could be moving north. You do another step, that could be moving north, or a different type of step, or east 1 unit at a time. At a time, but never in any other direction. So you're not allowed to move northeast. You're not allowed to move, and especially you're not including south or west. Okay, so all we can do is move north or east. So let me just, by example, show what I'm trying to talk about. So here's an example of a north and east path. Let's say starting at from origin. I won't end at 5, 3. That's just too much for a first example. Ending at 3, 2. So I'm going to draw XY axes. And so let's see. I'm going to use the lines that are kind of, I hope you can see those blue lines. Yeah, I can see that those blue lines are okay. And then so I'll try to draw, let's see, 3. So there's the point 3, 2. And here's what I mean by a north and east path. So starting at the origin, you can move to the right 1 unit. That's an east move. Your second move could be a north movement, and your third move could be an east movement, and your fourth move could be a north movement, and your fifth move could be an east movement. That works. So this zigzaggy path. But here's another one. So that's going to be considered one. Here's another north and east path. So the 1, 2 again, 1, 2, 3. So we need to end there, and we're only allowed to move north or east 1 unit at a time. So for instance, again, starting at the origin, you can move east, and then you could choose to do 2 norths. North, north. But as soon as you've done 2 norths, Well, you can only go north or east, but you can't. I mean, if you go north anymore, you have a problem, right? Because you were never allowed to go south. So at this point, we've gone north all the way up to 2. So now in order to reach here, but only moving north or east, we just have to move east. As another option, here's another north and east path. 1, 2, 1, 2, 3. So another option is to move north for a unit, and then move north for a unit, and then you have to move east three moves entirely. No other options, right? So the thing to notice, at least even in this smaller example, please note that all the north and east paths from the origin to the point 32 have a total of 5 1-unit movements. So I don't know if the picture is all that clear if I scroll back up just a little bit. So you see all 3 of these paths that were drawn in blue. In each case, there are 5 blue arrows. Is that we cool with that? So I mean, I just chose going up to the point 32 just for the sake of demonstrating something smaller, but I want to go back to our original 5.3. So starting at the origin, ending at 5.3. And so we'll make a similar statement here that all north and east paths from origin to 5.3 have 8 steps total, right? Just like over here, the 5 was obtained as 3 plus 2. So there should be 8 steps total. But if you can only move norths and east, and you're not allowed to move in other directions, just norths and east allowed, and that's it, then I hope you see, even from our smaller example, like here, I'll say that with 3 up steps, 3 up steps or 3 north steps, and 5 right steps or rightward or east steps. Just in case you're curious, why not allow souths and wests? I just don't want the silly business of to draw this in red here. If you went east and you went east and you went east, I want this to be a trap where you have to just go north and north and that's it. If we didn't allow that, then you could just kind of keep driving around the block forever, and then there'd be an unlimited number of paths. All of the sets we're trying to describe need to be finite sets. So. I hope it's clear. If you can only travel north and only travel east, and we are always starting at this point and always ending at this point, and that's it. Only traveling north, only traveling east. There's only a finite number of paths. You're gonna run out. Think about this like city blocks, right? So there's 0, 0. Here's 5, 3, and you can drive. You're only allowed to drive north and east from like school to home or whatever, right? Once it's like a city grid system, and once you've driven enough days and you're like, I'm going to drive a different way today, I'm going to drive a different way tomorrow, you're going to run out. If you can only drive in this grid, there's only so many ways you can do it without driving around the block. So you're only driving norths and easts. So here's the thing about this. These paths, they are in bijection with strings of length 8. Some extra restrictions about the strings I'm talking about. Consisting, not only are the strings of length 8, the strings are consisting entirely of N's and E's. So it's like, just pretend you have an alphabet where there's only 2 letters, N and E. Those are the only letters, and you make words, but the words have to be length 8. Okay, and not only that, with exactly 3 N's and the rest are going to automatically be e's. So just, I'm describing this bijection in words, but I'd like to really try to clarify, just like we did in the last example, by providing a specific example here. So I've got here on the y-axis up to 3, on the x-axis up to 5, 1, 2, 3, 4, 5. So we have to end here, right? And I would like to describe to you one north and east path. The specific one I have in mind starts at the origin, then you move east, then you move up, then you move to the right twice, 1, 2, then you move up once, and then you move to the right twice, and then you have no choice. You have to move up, right? So this specific north and east path that starts at the origin and ends at 5, 3, I'm going to say, according to the bijection I'm trying to describe, this maps to E, N, and then we went right twice, so E, E, then we went up once, so N, excuse me, then we went right twice, so E, E, and then N. Okay, so I'm going to leave it to you to think about. So I hope just even as I talk through it that you see what bijection I'm trying to describe. You've got to work through the thoughts of, is this truly a bijection? Does every path that you could have drawn over here really end up creating a string that has length 8 and has 3 ends and 5 e's, or the rest e's, let's say. And in addition to that, does every string where you only have ends and e's, but 3 of them are ends and the remaining 5 spots are e's, does that really build a path that would be an north and east path that starts here and ends where it needs to end? So those are some things I want you to think about. What I want to do is then I want to apply yesterday's techniques, and I want to say, let's count now. So if that really is a bijection, you've got to think about it, but later, right? So then how many strings made with ends and e's only? Okay, nothing else. Ends and e's only of length 8 have exactly 3 ends. Now I'm only just focusing on the 3 ends because if we know that there's got to be 3 ends and the string only has ends and e's, the rest of the spots have to be e's. So I'd like to think of it this way and connect it to an idea we saw yesterday. Let's talk about a string of length 8. It has 8 locations, I'm going to say. I'm being a little informal with this, but what I mean is like 1, 2, 3, 4, 5, 6, 7, 8. Think of it like a game of hangman, right? And in these 8 spots, each of the 8 spots are either ends or e's. That's what this part's about. But in addition, there's exactly 3 ends. So of these 8 locations, this is the strangest game of hangman ever, right? But of those 8 locations, 3 of these are ends. So look, here's the thing. Out of the 8 spots, you choose 3 of the spots to be ends, and the rest are e's automatically. So there are 8 things on the menu, and you pick 3 of them. The order doesn't matter. You're just picking the location of the 3 ends, and that, folks, is 8 choose 3. Right? So there are 8 choose 3 strings that consist only of the 2 letters N and E, where the strings are all of length 8 and have exactly 3 ends. You're just choosing the locations of the 3 ends. Okay, and so that's the codomain of this bijection. So there are, as well, there's, because of the equicardinal business, there are 8 choose 3 north and east paths from the origin to the point 5, 3. Ooh, that's kind of strange, right? But I hope that kind of works for you. I'd like to do one more. Just again something kind of entirely different. I want to get your thoughts flowing for like how this type of problem goes by giving you something different. So you have 7 pieces of candy. And 4 friends. And let's just say you must give away all the candy. So how many ways are there to distribute the candy? If you have to give it all away to your friends. And just as a note, for the sake of this, you can give all 7 pieces to friend 1. So we'll just name them friend 1 through friend 4, right? So you can give all 7 pieces to friend 1 and none, if you want, you can give none to friends 2, 3, and 4. Okay. However, that's going to be considered different. We'll count it as a different situation than giving all 7 candies to friend 2. So what I'd like to do is describe to you in words and by example show you what this bijection is trying to do. I'd like to describe a bijection from the set of all possible situations. Let me underline that phrase, the set of all possible situations. So giving all the candies to friend 1 is one element of the set that I just underlined. Giving all the candies to friend 2 is another element of the set. So situation this is a set of situations. And then 2, the codomain, is the set of strings of length 10 with 7 C's and 3 vertical lines. Okay, so set of strings of length 10 with 7 of the characters being C's and 3 of the characters being vertical lines. Let me describe this bijection. Okay, so I want to do this actually by example. So let's look at the situation of you give 2 candies to friend 1. You give 2 to friend 2. You give 2 to friend 3. And, well, friend 4 is a little unlucky. 1, the remaining candy, 1 to friend 4. So in words, let me box this. That's the situation I'm describing. Okay, that's one element in the domain. And what's it going to map to? The following string, CC, vertical bar, CC, vertical bar, CC, vertical bar, C. I'm going to describe another situation. Let's say you give 4 candies to friend 1 and 1 each to the rest. So friend 1 gets 4 candies, friend 2 gets a candy, friend 3 gets a candy, and so on. What string is this going to map to? C, 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 bar, C, bar, C, bar, C. So what I want you to do, I know it's just 2 examples. You're like, whoa, this is so unusual as a format. But I want you to, with the 2 mappings as examples, think of the vertical line that's drawn as a divider line. So what I'm trying to get at is, let's say the number of C's, let's try that again here. The number of C's before the first vertical line is drawn is how many candies friend 1 gets. So notice here, like even in these examples, CC, and then there's the first vertical bar. That's how many two candies for the first friend. In the second example, 4 C's before the first vertical bar. That's how many candies friend 2 gets. Right? And then here, then the number of C's between the first bar and the second bar is how many candies friend 2 gets. You only need 3 vertical bars. If you have 4 people, you only need 3 vertical bars. So let's make some sense of this. I think describing a couple other examples should help clear this up a little bit. So all 7 candies. Let's say you just have a favorite friend. All 7 candies to friend number 1. That's another situation. So let me box this text. We have to describe the situation in words. The string this maps to is C, 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 C. So 7 candies to friend 1, bar, bar, bar. No candies for anybody else. All 7 candies to friend 3. What would that look like? Well, person 1 doesn't get any candy, so a bar. Person 2 doesn't get any candy either. Bar. If the first person got any candies, there would have been C's written before that divider. Had the second person received candies, there would have been some C's in there. But instead, it's 1, 2, 3, 4, 5, 6, 7 C's, and then one more vertical bar. All 7 candies to friend 4. It should be bar, 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 then 1, 2, 3, 4, 5, 6, 7 C's. So this takes a lot to process, but I want you to think about independently why you only need 3 vertical bars. You don't need 4 vertical bars. That would create sort of 4 separate spaces, right? Like, so they would create 5 separate spaces. When you just have 3 vertical bars, like let me just draw the 3 vertical bars spaced out. Then there's room here to write the number of C's necessary for the first friend, the number of C's necessary to represent the number of candies for the second friend, the number of candies for the third friend represented by how many C's are written, and then after the third and final bar, there's space to write down C's for the fourth friend. So for 4 people, you only need 3 vertical bars. In fact, if you had any more than this, you're not going to really create a bijection. So it takes some processing and thinking through, but I just want to maybe comment on it, and then you've got to think about this. If there are 4 friends, 4 people receiving candies, I want you to think about how see that you only need need 3 divider lines. If you're kind of unhappy with this, reduce it down from the situation of, okay, different problem, but think about, instead of 4 friends, think about just 2 friends. Right? Think about how you only need 1 dividing line, in that situation. And so then here's another thing that I want you to think about. It's one thing to come up with the rule, and I wanted to spend a lot more time today talking about the rules, and then I want you to think about why the described rules really are bijection. So here's what I'll say about it, and here's what I challenge you to think about. Each situation, distributing candies to the 7 candies to the 4 friends. Each situation corresponds to 1 string of length 10 with 7 C's and 3 vertical bars. Right? Every situation is going to go to a different string, and then the other thing is each string of length 10 with 7 C's and 3 vertical bars describes a situation. And it describes a different situation. So this is all in words, but in words, these 2 bullet points are trying to address the idea that this function, if you truly believe it is a function, first of all, then it is a bijection. And the number of ways. Well, let's think about this. So the thing is, this idea. So the codomain here, strings of length 10 with 7 C's and 3 vertical bars. This is like the north and east paths in just one sense, in that you've got a string of length 10. There's only two possible characters. Earlier it was N's and E's. Now it's C's and bars. But the number of ways this should occur is there's 10 locations, and you choose 7 of the locations to be C's. Right? So this is the number of strings of length 10 where you choose. I'm trying to use the word choose very decisively here. You choose 7 of the locations to be C's, and the rest are automatically. The remaining 3 spots are automatically divider lines. Okay, so if the strings of length 10 with 7 C's and 3 bars, if there's 10 choose 7 of those, then in the end there's 10 choose 7 possible ways it could have ended, of starting with 7 candies and giving it all away to the 4 friends. There's 10 choose 7 ways it could have ended. All right, questions? I guess we're done because of the blinking, but let me know if you have thoughts or reactions or complaints. I can stick around here for a bit. Not too long, but I can.